Welcome to this video. My name is Mark Scythian and the date today is January 9th, 2025. So this lecture is going to focus on DC electromotive resistor circuit motor performance. So let's say we have this DC series parallel complex circuit and it's taking a certain voltage and current from a DC electrical power source to power a DC electric motor. So we'll populate the resistance values of each series and parallel resistor accordingly. So the design goal inquiries are calculate the motor's brake horsepower, calculate the motor's foot-pounds torque, and lastly calculate the motor's RPM. So we can't create or destroy energy, we can only change its form. So the electrical power will be manipulated through the circuit and then ultimately converted to mechanical power at the output of the electric motor's drive. So we start at the midpoint of the circuit where positive flow transitions to negative flow. So practically on the right side of the circuit, and we combined the first two parallel resistors, R7 and R8. We combine these in parallel using the inverse sum law, and we calculate a combined resistance of 1.2 ohms. Next, we take that combined resistance and we combine it in parallel with R6, 15 ohms, and we get 1.1 ohms. Next, we combine R3, R4, R5 cluster in parallel into a combined resistance value equal to 0.027 ohms. So now we add that combination to the 1.1 ohm combined resistance in series together, and then the combined resistance value is absorbed into the R6 zone, which is then combined in parallel with the resistance at R2. So this is combined in parallel, so we use that inverse sum law and combine both accordingly. Then we yield 1.01285 ohms. So we use 5 significant digits for initial precision but final accuracy. So now all we have left is the series addition with our 1.5 ohms. So we add these together and we quickly calculate a total resistance of 1.51 ohms. Now you could in the real world just use an DC ohms meter at the positive and negative points, for which the electricity flows only from positive to negative. So you'd get 1.51 on the ohm meter. You know, the total voltage is 36 volts. So if we use Ohm's law and divide the total voltage into the total resistance, we can calculate the total current coming from the positive terminal. So that's 23.84 amps. So we trace that amperes flow from the DC power source. So the circuit functions to extract a portion of the total current available at the DC power source. For example, it might be a 1,000 amp battery, but we only want 23.84 amps out of it. So we build the circuit to do just that. So the series electricity from the positive terminal flows in constant value across the R1 series pathway and multiplies itself times 0.5 ohms resulting in an 11.9 volt drop from the source. So this means we subtract 11.9 volts from the 36 volts, and then 24.1 volts flows to R2 in parallel, which then divides itself into the 10 ohms to extract 2.41 amps at R2 away from the 23.84 on the first node across R1. So essentially R2 takes away the current flow at R1. So this leaves us with 21.43 amps going to the R3, R4, R5 cluster. These are on series, but they are combined in parallel. So typically cluster resistors are to dissipate greater heat and lessen the wear on the circuit. So we can add these three in parallel, or combine these three actually. Inverse sum law for combining parallel resistors. And we calculate 0.027 ohms as the combined resistance value for R3, R4, R5. And then we can multiply the 21.43 amps times the R3, R4, R5 combined resistance, and we get a 0.57861 volt drop taken away from the 24.1 volts. So this leaves 23.5 volts at R6, dividing itself into the resistance at R6, 15 ohms, taking away 1.57 amps from the 21.43 amp source on series before R6 junction. This leaves 19.86 amps. And so we combine R7 and R8 in parallel. We get 1.2 ohms, but we don't have any resistors on series before the R7, R8 cluster on parallel. So there is no voltage drop from 23.5 volts. This will transfer in constant value to the R7, R8 cluster and divide itself into the 1.2 ohms combined resistance to take away 19.58 amps from 19.86 amps. This leaves us with 0.28 amps that flows to the motor. And then that also leaves us with 23.5 volts DC flowing to the motor. So if we were to multiply the volts times the amps, we'll get the electrical power input into the motor. Then we multiply that value times the efficiency, 0.72, and then we get the mechanical power output at the motor. So this is 4.73 watts of mechanical power. And then we divide that value into 746 watts per horsepower, and we calculate 0.0063 brake horsepower at the motor. And so now we solve for the meters radius at the output drive, which has a 0.125 inch diameter. So we divide that into 2 to get 0.0625 inches radius. Divide that into 12 to get feet, and divide that into 3.28 to get meters. So we have a 0.001588 meter radius for the drive output. And then 4.73 watts is actually 4.73 Newton meters per second, but we can just use the torque value per second. So then multiplying that times updated meters radius, rather than just 1 meter, it's going to be 0.001588 meters. So this actually converts a torque of 0.006558 Newton meters of torque. There is 1.36 Newton meters of torque to 1 foot-pound of torque. But we can take a pause there and then now figure out the angular velocity, which is the power divided into torque in the metric values of systems measure. So we have 4.73 watts divided into the 0.006558 Newton meters. We calculate 721.26 radians per second. We can then convert the Newton meters torque value to foot-pounds. and we calculate 0.048 foot-pounds of torque. Then we convert the 721.26 radians per second into revolutions per second. 2 pi radians per revolution is 360 degrees, so we just divide that into 2 pi. We get 114.8 revolutions per second times 60 seconds. So that's 6,887.5 RPM. So again, this is just another exercise in the conservation of energy. We can't create or destroy energy, we can only change its form. So we build devices and machines, etc., to convert one type of energy to another, in this case, electrical power to mechanical power, but articulated through a circuit design. Thank you for watching this lecture and have a great day.